All right, well, hello everyone, and welcome back. In this extra video, we will be introducing digital logic and computer architecture. These two are extra topics that we briefly introduce in this course, and you'll learn about them in much greater detail if you take additional electrical engineering or computer engineering courses. So here our goal is to just provide a brief introduction, and hopefully you'll find this stuff interesting and worth learning more about. If you haven't already done so, please make sure that you review our previous video introducing devices so that you remember the basics of semiconductors and diodes. This video continues where our previous lecture left off. So here's our goals for today. After watching this video, you should have a better idea of how transistors can be used as building blocks to create digital logic circuits in computers. If you want a review about how transistors work, definitely check out our previous lecture where we introduced devices. In this video, we're focused a little bit more on applications. So we'll learn about how we can convert numbers between binary and decimal form. And we'll also look at how circuits can be used to perform logical calculations. We'll learn about some building block circuits like logic blocks, latches, flip-flops, adders, and counters, and we'll see some simple examples about how these circuits can be used to create computers and memory. Throughout these slides, you'll notice that I've included some references to other websites and books and sources, and I recommend that you check these out for additional information. There's also a lot of really good simulations online, which I've linked to in our extra resources. I definitely recommend that you check out those simulations to also help visualize these different topics. Let's start with a quick review question. Last time we learned about ideal diodes. And so in this review question, let's just go ahead and ask ourselves whether this ideal diode will be conducting in the circuit shown. And you'll notice that we are given some information about the circuit. We know in this case that Vs is 12 volts. We know Vb is 11 volts. R1 is 5 ohms. And R2 is 4 ohms. Our goal here is to determine whether this diode is conducting. So let's first start with a little bit of strategy. You'll remember that to be conducting, we must have a positive or zero bias voltage across our diode. So the best approach for these types of problems is to do the following. First, we will replace the diode with an open having VD across the terminals. Then we'll solve for VD. And based on the value of VD, we can figure out whether that diode is indeed conducting or non-conducting. You'll see that when we solve for VD, we'll actually be able to use node analysis in some of our basic DC circuit techniques. So let's give this a try. So let's go ahead and try that approach. where we replace VD and the diode with an open circuit. And so in this case, we'll get something like this. So notice we've got our voltage sources, and we also have our resistors. And we want to solve for VD, where VD is in the polarity shown. Well, how would we solve for VD in this case? There's actually several different approaches we could try. For example, we can do Kirchhoff's voltage law. We can try combining those voltage sources into an equivalent source. There's multiple different options here. You can also even consider doing some classic node analysis. So in this case, one thing we can notice is that there's going to be some current I flowing through this circuit. I'm not sure what direction yet, but I know there's going to be that current I. And we also know that we are going to have some voltage sources here that could be combined. I'm going to go ahead and apply Kirchhoff's voltage law to the outer loop. So I'm going to go ahead and just apply Kirchhoff's voltage law, and I'm going to walk clockwise around the loop. And here my goal will be first to solve for that current I. Because once I know what that current I is, then I can use I to determine VD. So if I apply Kirchhoff's voltage law, let's see what we get. First we have plus 12 volts. Then we walk across our 5 ohm resistor in the direction of I. So I'm going to go ahead and write my voltage across the 5 ohm resistor as minus 5 times I. Similarly, voltage across my 4 ohm resistor becomes minus 4I. And then I have minus 11 volts. So I know by Kirchhoff's voltage law that everybody must sum to 0. Notice that I can combine like terms. And I see here that plus 12 and minus 11, that becomes 1 volt. That will equal 9I. Therefore, my current I is going to be equal to 1/9 amperes. So now I can go back and actually determine what VD is. Notice if I apply Kirchhoff's voltage law around a smaller loop, on the left loop, I know that plus 12 volts minus 5I, then notice the sign here, it will be plus VD will be 0. So therefore I can say plus 12 volts minus 5/9 plus VD will be 0. And then in this case, if I go ahead and solve, I can determine that VD will actually be equal to approximately negative 11.44 volts. So wait a minute. Based on VD, are we conducting or non-conducting? Well, in this case, since VD is negative, the diode is not conducting. So notice how our good old-fashioned Kirchhoff's laws and DC circuit techniques allowed us to determine how this diode will behave. Our strategy was to first assume the diode was not conducting, figure out how much voltage was happening across that diode, and that allowed us to determine the behavior of our diode. Remember, for an ideal diode, as long as the voltage is not negative, we're conducting. In this case, our ideal diode indeed had a negative voltage, so in this case, because our voltage is negative, our diode is not conducting. So let's go ahead and continue where we left off in the previous video. In the previous video, we introduced this idea of computer architecture. And we defined computer architecture as the design and organization of components making up a computer. And so our key takeaway from last time was that by combining transistors, diodes, resistors, and digital logic circuits, we can actually create circuits that are able to do calculations, create memory, and even build computers. So in this video, let's take a closer look at how we would actually do this and what these building blocks are. So first, let's define a couple important terms. You'll remember before that an integrated circuit is defined as a collection of electronic devices interconnected on a single silicon chip. We mentioned how this makes our circuits a lot more robust and compact, and makes it a lot easier to take these circuits and combine them with other parts into a finished product. We've also previously introduced analog and digital signals. Remember that analog signals can have a wide range of potential values, and often they vary in proportion to some physical quantity. On the other hand, digital signals can only take a finite number of values. Common example is the binary signal, where binary signals can only have one of two possible values. And often in a computer, we work with binary numbers, which are either zeros or ones. Let's cover a few more key terms that are especially important in computer architecture. In computer architecture, we define a bit as a single digit in a binary signal. Here we are specifically working with zeros and ones as the two options that our binary signal can have. A byte is defined as a set of 8 bits. And then, depending on our conventions, we often define the least significant bit as the rightmost bit in a binary number, and the most significant bit is the leftmost bit in a binary number. We'll see how this works in just a moment. But please make sure you remember these terms. This brings us to our next point, the binary number system. Many of our circuits in computers and logic circuits operate in states of being either on or off, or being 1 or 0. And so when we create logic circuits, we often design our circuits to use those binary numbers and binary signals. So engineers have developed this system of binary numbers, which are numbers based on powers of 2. This is different than our decimal system, where the numbers we're familiar with in most normal settings. Most of the time we work with decimals that are based on powers of 10. For example, the number 4 in decimal form would be written as 100 in binary. How this works is we're basically saying that the number we're trying to encode, 100, is equal to 1 times 2 to the second plus 0 times 2 to the first plus 0 times 2 to the 0. So therefore we get 4 plus 0 plus 0, or 4. Similarly, the number 15 is actually written as 1111, because in this case, we actually write 15 as 1 times 2 to the third, plus 1 times 2 to the second, plus 1 times 2 to the first, plus 1 times 2 to the 0. So we see that that will give us 8 plus 4 plus 2 plus 1, which gives us 15. Or, for example, number 9 would be written as 1001, or 1 times 2 to the third, plus 0 times 2 to the second, plus 0 times 2 to the first, plus 1 times 2 to the 0, which gives us 8 plus 0 plus 0 plus 1, or 9. So let's go ahead and show how to convert between whole numbers and binary numbers using an official procedure. So one of the easiest ways to convert a whole number to binary is to use what we call successive division by 2. Essentially what we do is we divide the number to be converted by 2. And the remainder from that first step is the least significant bit, or the last digit, of our binary number. And we keep dividing and dividing and dividing until our quotient becomes 0. The remainder of that last division is our most significant bit, or the first digit of the binary number. And we read our result from the bottom up. So in this case, you would see that the number 29 becomes 11101. So if we write that as powers of 2, notice that's the same as writing 1 times 2 to the fourth, plus 1 times 2 to the third, plus 1 times 2 to the second, plus 0 times 2 to the first, plus 1 times 2 to the 0, which gives us 16 plus 8 plus 4 plus 0 plus 1, which gives us 29. So basically, we're rewriting a decimal number as the sum of powers of 2. So let's go ahead and do an example converting 10 to binary. So essentially what you can do is you can follow an example like here where you draw it in tables, or you can just divide. So if I have my number 10 and I want to divide by 2, 10 divided by 2 is 5. And then the remainder is 0. So therefore, the remainder from step 1 will be the last digit of my binary number. But next, I need to divide 5 by 2. 5 divided by... So next, remember, if I divide 5 by 2, I do get a remainder, so I get 2 remainder 1. So the 1 becomes my second digit, or second to last digit. Now I take the 2, and notice I don't get a remainder when I divide 2 by 2. So my third to last digit will be 0. And finally, I take that 1 and I divide my 1 by 2. I get 0, remainder 1. So therefore, my very first digit will be 1. So now I read backwards, and I determine 10 is equal to 1, 0, 1, 0. It's 1 times 2 to the third, plus 0 times 2 to the second, plus 1 times 2 to the first, plus 0 times 2 to the 0, which gives us 8 plus 0 plus 2 plus 0, or 10. So whichever approach is easier for you to track, the key thing to note here is you just want to make sure that you accurately write your decimal number as the correct sum of powers of 2. So how do you handle decimals then? So it turns out if you have a decimal number, the approach is very similar. What you do is you first process the whole number portion using that successive division we demonstrated. And then you use a slightly different approach for the decimal places. Instead of dividing the decimal places by 2, you multiply the decimal places to be converted by 2. And if the product is greater than 1, we call the carry 1. If the product is less than 1, the carry is 0. And this first carry value is the first digit of the binary number's decimal. And you basically keep multiplying and carrying until you end up with a product of 0. And that last carry you get will be the last digit of your binary number. And so notice that if you are actually writing your final number in binary, you just put the whole number part and then a decimal point, and then you write the decimal part. Here's an example of how you would convert 0.375 to binary. So our first step would be to multiply the number to be converted by 2. So 0.375 times 2 would be 0.750. So here, 0.750 is less than 1, so our carry is equal to 0. And so we keep multiplying until the decimal places become 0. So the second round, we take our 0.750, we multiply that by 2, we get 1.5. So this time, our carry is equal to 1, because 1.5 is greater than 1. So notice for this third step, we take our decimal places, which is 0.5, we multiply by 2, we get 1. So our carry here is 1, and our result is 0. And we stop. So notice in this case, the first time we ran this calculation, we got something less than 1, so we know that our first digit of our result will be 0. Our second carry was 1. Third carry was 1. And then we stopped. So therefore, our correct answer is 0, 1, 1. And we would see that this would actually give us the correct result, because if we say 0 times 2 to the negative first plus 1 times 2 to the negative second plus 1 times 2 to the negative third, we would see that 1 times 2 to the negative 2, that gives us 0.25. 2 to the negative 3 gives us 0.125. So 0.25 plus 0.125, that gives us 0.375. So if you read the digits in the correct order and perform the division correctly, you'll get the desired result. Finally, as we saw, it's actually very easy to convert between binary and decimal numbers. All you have to do is add powers of 2. So you add powers of 2 for the position where each binary value is 1, and we ignore the powers of 2 for each position where the binary value is 0. For example, here, 1, 0, 1, 0, 1, that's the same as writing 1 times 2 to the fourth plus 0 times 2 to the third plus 1 times 2 to the second plus 0 times 2 to the first plus 1 times 2 to the 0. That gives us 16 plus 0 plus 4 plus 0 plus 1. That gives us 21. So most of the time, it's actually not necessary to do these calculations by hand. You can actually have Windows or an online calculator do binary for you. For example, if you open the calculator app on a Windows computer, you can see there's this programmer calculator option, and it will actually allow you to do calculations in binary. Alright, so let's go ahead and try this example. In this case, we want to convert these numbers from binary to decimal format. So we've got 1101 and 1.01. Let's give this a try. So our first number, 1101, this number needs to be written in terms of powers of 2. As we've demonstrated, we write the number as the following. So notice we take our binary number and we multiply the power of 2 by that value. Then we sum our powers of 2 to get our final answer. So in this case, 1101 is equal to 1 times 2 to the third, or 8, is 1 times 2 to the second, which is 4. 0 times 2 to the first is 0. And 1 times 2 to the 0 is 1. So 8 plus 4 plus 0 plus 1, that gives us 13. Let's go ahead and try our second number, 1.01. We want to convert this to decimal format. So first, let's consider the whole number part. So here we have, first we have 2 to the minus 2, 2 to the minus 1, and 2 to the 0. So in this case, our whole number part, that 1, that becomes 1 times 2 to the 0, or just 1. Our decimal, on the other hand, is a little different. Remember, our decimal becomes 0 times 2 to the negative 1 plus 1 times 2 to the negative 2. That gives us 0 plus 1/4, or 0.25. So therefore, 1.01 in binary is equal to 1.25 in decimal format. So notice these calculations aren't too bad once you get the hang of it. And most of the time you can use a binary to decimal converter, but it's good to know where these calculations came from, because these are the calculations that our transistor circuits and digital logic circuits are actually performing. Alright, so in our next example, let's explain this silly engineering joke. There's this joke that says the following. There are 10 kinds of people in this world. Those who understand binary numbers and those who don't. Why might this joke be funny for someone who understands binary numbers? Well, let's take a look at 10. In decimal form, 10 is the number 10, but in binary, what is 10? Well, in binary, In binary, one zero is equal to 1 times 2 to the first plus 0 times 2 to the 0, which is equal to 2 plus 0, or 2. Therefore, this joke is just kind of poking fun at the fact that 10 is the number 2 in binary. So there are indeed two kinds of people in the world, those who understand binary numbers and those who don't. And hopefully now, after seeing these examples and doing a few practices yourself, you will see that you're one of the people who now understands binary numbers. So it turns out that there is actually a whole bunch of rules established for doing math in binary. And you might be thinking, well, why would we bother doing math in binary? Why don't we just do math in decimal numbers like we're used to? Well, decimal numbers are great if you are human and have a brain and you know how to use decimal numbers. But if you are an electric circuit that only knows how to be on or off, then binary is your only option. And so it turns out that in electric circuits, we actually have to do math using binary and using the rules listed in these tables. So you can see there's a bunch of special rules for addition, subtraction, multiplication, division, addition, and multiplication. And so circuits actually use these rules in order to do math. So I don't expect you to memorize these rules for the purpose of this course. However, you'll see that in future courses you might take, these rules can become really important. I recommend that you check out some of the references in this slide if you would like additional details and additional practice. So as we mentioned, circuits need a different type of math in order to do calculations. Circuits can't just do math with decimal numbers. They have to do math using binary. And so this brings up a whole field called digital logic. And so when people first started doing math with circuits, we needed to come up with ways of doing math. And that's where Boolean algebra comes from. Boolean algebra is the mathematics associated with the binary number system. And it's also very closely related to digital logic. This system is named after George Boole, who was one of the people who developed the system. And so we call Boolean variables variables that are represented by either a 0 or a 1. 0 is sometimes called false, 1 is sometimes called true. Basically, this is simulating a circuit being powered on or off, or a transistor reading on or off. In addition to encoding numbers, we can also perform logic calculations. So logic functions are functions or equations that contain Boolean variables. When we're doing math with Boolean algebra and Boolean values, we often make what's called a truth table. A truth table is a listing of all the possible values that each Boolean variable can take. And basically, it's listing out every possible value of that resulting function. Another important term to know is this thing called a logic gate. Logic gates are physical devices, like circuits or transistors, that are used to perform logic functions. So keep these key terms in mind as you finish up our remaining lab assignments. So you might be wondering, well, what kind of logic gates and logic functions can we actually make? And so in this case, for our class, we're just going to treat these logic gates as black boxes, but we'll see that each of these gates is made out of dozens of resistors, transistors, and diodes combined together. And so we can create things like or and, where if either input is true, then the output must be true, or if both things are true, then the output is true. And so if you've done any computer programming before, you may very well have used some of these functions to help perform logic or make decisions. So for example, not will reverse the logic variable. And then, of course, we have NAND, NOR, and exclusive OR, where these are the AND OR followed by an inverter. So these are the basic logic blocks, and it turns out that each of these logic blocks can be used as a building block in order to perform calculations in a computer. So here our goal is to just briefly introduce some of these topics, and if you take more courses on this digital logic in the future, you'll likely run across De Morgan's theorems. De Morgan's theorem says that any logic function can be implemented by using only or and not, or by using only and not gates. And so here's an example of what these functions would look like. For example, here, suppose I wanted to make a truth table for and, or not gates. Basically, in a truth table, you list all the possible values of the inputs, x and y. So if both x and y are 0, then my z is 0. And notice that the AND function is only true. It only gives us 1 only when x and y are 1. Similarly, OR will behave kind of in the inverse way, where as long as somebody is 1, we will get 1 as our output. If everybody is 0, then we get 0. So for the purposes of this class, I'm not going to ask you to do truth tables on the final exam, but I do expect that you know what a truth table is. Truth tables are basically used to help predict the outputs of logic functions. And we can use them to design digital circuits to perform logic calculations. Here's some examples of what the truth tables would look like if we had the NAND, NOR, and exclusive OR. So you can see what happens is if we take the AND and we follow it with the inverter, then we do indeed invert our output in the finished result. So you might be wondering, well, why do we actually need these ANDs and ORs? And the reason why is because we use these AND and OR logic blocks in order to actually do Boolean algebra and perform math with binary numbers. So here's an example of how we can actually design a circuit to perform math. This half-adder circuit actually performs binary addition. So we have two inputs, A and B, and it will output a sum and a carry bit. And this half-adder is not able to take a carry in the input, but notice that depending on what our inputs are, A and B, we will get a sum and a carry. So we can actually design a circuit that will take two inputs and give us the sum. Of course, this is following Boolean algebra rules. So we call this a half-adder because it's actually only able to add just the input bits without any carry value in the input. But if we look back at our Boolean algebra rules from earlier, sometimes we do need to account for a carry value when we are doing math. And so in order to compensate for that, we also have this circuit called a full adder. And the full adder can actually perform that complete 2-bit addition. So it can take a single 0 or 1. So it can take 0 or 1 in input A, 0 or 1 bit in input B, plus a carry bit from a previous operation, and it will give us the corresponding output for the sum and the carry. And you can see that this truth table actually lists out all the possible operations for this full adder. You see that if A, B, and C are all 0, then our sum will be 0. But depending on the combination of A, B, and C, we will get the result following Boolean algebra rules. Here's another example of some digital logic circuits which are commonly used. Very often we have many different signals in our circuit at a given time, and we need to be able to direct data from place to place. So we have these circuits called muxes or DEMUXs, or also known as multiplexers or demultiplexers, and these allow us to combine and split inputs. So for example, the mux will actually take inputs and combine them into one. Whereas a DEMUX will actually split inputs into outputs. So these are really important when we want to direct data to elsewhere on our chip. You'll notice that this mux will allow us to selectively send one of its inputs into that output, and the DEMUX will take its single input and send it to one of our outputs as desired. So it's really important to be able to direct our data if we're doing some complex calculations. Another very important feature in computers and digital logic is memory. And here we'll just briefly introduce a few terms that come up when working with computers and memory. One term that's very important is a combinational logic circuit. This is defined as a circuit whose output depends only on the circuit's present inputs. We say that this circuit has no memory of the past, because all it knows, all it cares about, is the present inputs. However, it's also possible to have a circuit called a sequential logic circuit. And this is a circuit whose output can depend on the circuit's previous states as well as the present inputs. So this circuit actually does have memory of past states and past inputs. So how do we actually make a circuit have memory? To make a circuit have memory, we have to include feedback paths. So we route the output from a gate back to the input of an earlier gate. So if we have feedback loops in our circuits, this allows us to create memory because we are sending data back into the past to influence calculations. So there are some special circuit components called latches and flip-flops which have those feedback paths. And so we use latches and flip-flops to help us create memory and sequential circuits. So the main takeaway you should remember for our purposes is that every latch and flip-flop is a memory device that can store a single bit, so either a single 1 or a single 0. And often, when we work with latches and flip-flops, we use these terms set and reset. So if we set a latch or flip-flop, that means we set its output to 1. When we set the output to 0. And you might be thinking, well, how and when would we want to use these things? There's many applications of these circuits in developing memory. A common one is counters. And so you can actually take flip-flops and latches and create circuits that count up or down. And we'll take a look at a simulation of this in lab, where we see a synchronous up-down counter. And these circuits can actually count, starting with 0, and they can go all the way to the maximum value allowed based on the number of bits. For example, you see that if this is a 3-bit up-down counter, if I have 3 bits that can be 0 or 1, that means if all my bits are set to 1, I can count You'll notice I can actually count 1 times 2 to the second, plus 1 times 2 to the first, plus 1 times 2 to the 0. So you'll see, in this case, I can actually count 4 plus 1, 4 plus 2 plus 1, or I can count to 7. If I have more bits, I can count to an even higher value. For example, a 4-bit counter would allow me to count starting from 0 all the way to 15, because I would also have an 8 from 2 to the third. So these counters can be really important in developing memory and developing circuits able to do more complex tasks. So this concludes our brief introduction to computer architecture. Here we're just scratching the surface of a very interesting and complex discipline. So if you find this stuff interesting, I highly recommend that you consider checking out our references and also consider taking some more advanced courses on computer architecture, computer engineering, or electrical engineering. Our key takeaway for this course is just to understand the basic key terms and ideas we've introduced. You can see that transistors, diodes, resistors, and the digital logic circuits we covered form the building blocks for the computers and electronic devices that we use. Let's go ahead and wrap up here for today. You should now be able to explain how transistors can be used as building blocks to create digital logic circuits. You should also understand how binary numbers work, and you should know how to convert numbers between binary and decimal form. You may need to do some of these conversions in one of our last labs. Finally, you should be familiar with the basic terms we covered, including logic blocks, latches, flip-flops, adders, and counters. I don't expect you to memorize the very specific details for the purposes of this class, but you should understand what these things are in case you see them in more advanced courses. Thanks everyone for joining the fun, and we'll see you in the next video.